the recording. So welcome everybody to the SNOLAB seminar. So today, today's speaker is Professor Justin Reed. He's the head of the physics at the University of Surrey. His main research area is gravitational probes of dark matter, studying everything from the tiniest galaxy in the universe, where we can measure our dark matter cluster on the smallest scale, to giant cluster of galaxies. He completed a PhD in theoretical astrophysics at the Cambridge University in UK. After 2-year postdoctoral research position also in Cambridge, he moved to the University of Zurich to join the computational science group. In 2009, joined the University of Leicester as a lecturer in theoretical astrophysics, and in 2010, he was awarded an SNF assistant professor at the ETH in Zurich. And then since April 2013, he took a full chair at the University of Surrey and was awarded 2013 Merak Prize by the European Astronomical Societies for his high impact research in computational astrophysics and cosmology. Thank you very much for being here. And today, Justin will discuss about galaxy formation simulation for probing the nature of dark matter. Thank you very much.
Thank you, Sylvia, and thanks for inviting me today. So let me just start at the beginning a little bit. So we have now what we call the standard cosmological model. And this model is sort of somewhat surprising because it throws up in our face what seems to be the result that most of the universe is dark. So 27% dark matter, 68% dark energy, and a mere 5% seems to be familiar atomic, or what I'm going to call baryonic matter. And this may seem odd, but that model gives a remarkable match to structure in the universe, and that's what I'm showing here. This is a plot of the power spectrum versus inverse scale. So we have small scales over on the right here and very large scales over here on the left, and these sort of very large scales are probed by the cosmic microwave background radiation, the afterglow of the Big Bang, and the error bars on that from Planck are now so exquisite that it's actually this little gray band. That's the real data, and the best fit model that has the dark matter and the dark energy in it is this thick blue line. And the data extends all the way up to here, where we start to enter the weakly nonlinear regime. So I've normalized this so that above about 1, we go from linear growth, so each bit of the universe collapsing independently of all the other bits, to what we call nonlinear growth, where collapsing bits of the universe start to merge with one another and overlap. And when we get to these nonlinear scales, we have to probe the CMB on ever smaller angular scales on the sky. And so we need to start using other data, because at some point the CMB data run out. And the good news is the universe is kind. There's plenty of other probes of structure. And probably one of the most competitive on these weakly nonlinear scales is called the Lyman alpha forest radiation. And here's some green data points from Zerubi et al. 2006 showing this here. And just to explain to you a little bit how the Lyman alpha forest works, this is a lovely movie from Andrew Ponson. The idea here is you look along the sight line to a distant bright quasar, and this arrow here represents the light from that quasar. And as that light travels across the whole universe, it pierces through lots of intervening hydrogen clouds. And most of that hydrogen is actually in filaments, or it's in between galaxies, but every now and then you'll puncture a galaxy as well. And in the rest frame of that photon, all that hydrogen gas is at different redshifts, okay? And so the same hydrogen lines, Lyman beta, Lyman alpha lines, get redshifted in the rest frame of that photon, creating this forest of absorption lines in the quasar spectra. And the basic idea is that the more intervening hydrogen gas there is, the more structure there is in the universe, and the more of these lines we'll see. So via some modeling, we can try and infer from the statistics of the forest of lines how much structure there is, and from that infer the power spectrum. And that basically gives us a rather nice probe down into these weakly nonlinear regime over here. Now, the reason this is interesting is once we start to get down to these really small scales over on the right here, we can actually start to see differences, different predictions from different dark matter models that we can actually go and test. So this blue model here assumes that dark matter is cold, which means it's non-relativistic at the time it decouples from the expanding universe. And an example of cold dark matter is, for example, Susie WIMP's, sort of classic cold dark matter candidate. But there's plenty of other well-motivated dark matter candidates that would behave differently. In particular, for example, sterile neutrinos, which are a sort of a warm dark matter candidate. So if you imagine some thermal relic particle decoupling from the expansion, if the particle is light enough, so in the sort of keV range, then it will free stream for a while. It will be relativistic for a small time, and that suppresses the growth of structure on small scales and at early times. And this is what we mean by warm dark matter. And you can see the suppression in the power here for this particular warm dark matter model, which is a 3 keV thermal relic. And so if you could probe the power spectrum over here, you could in fact distinguish this warm and cold dark matter model. And in fact, you can actually already distinguish it with the Lyman alpha forest data. It's hard to see here, but there are small differences between these two models that exist, of course, even on larger scales. And if you do this comparison more carefully, and you do it in data space rather than here in the power spectrum, the very latest Lyman alpha forest data actually does suggest at 95% confidence that dark matter is colder and therefore more massive than this 3 keV thermal relic. And there's quite some sort of debate around this, but I think most studies would conservatively agree with the sort of 3 keV bound at this point. But we'd like to go further, right? We'd like to really see how cold dark matter is, and if dark matter is warm, we'd actually like to detect the particle. And one way we could do that is if it's warm enough that it impacts structure formation on these small scales, we might see the imprint of that in astrophysical data. And there's several kinds of probes we can use to kind of push our measurements of this matter power spectrum to smaller scales. And the three main ones are what I'm going to call galaxy counts, strong gravitational lensing, and stream bumps. And I'm going to explain later on in the talk exactly how these work and what the latest constraints are and what the current limitations are, where we need to improve things. But before I get into that, in order to do anything over here on the right, to make these kinds of comparisons, we need to be able to predict what the power spectrum should look like for different kinds of dark matter models. I mean, I've shown you this red line on here and this blue line on here, but you'll notice that up here, we're here in the very non-linear regime. We're in this regime where structure's actually going to merge with itself, and we'll have all sorts of non-linear effects that are not included in these simplified models that I put on this plot here. And so to do this kind of comparisons properly and robustly, we actually need to follow that non-linear growth of structure on very small scales. And for that, we're going to need simulations. And that's really what I'm going to focus most of this talk on, trying to describe to you what these simulations are, what they can and cannot tell us, what the state of the art is, and then I'll come back towards the end as to what kind of constraints on dark matter we can get from all of this. So let me just start with pure dark matter simulations. Now, these are a simpler place to start because pure dark matter simulations model just the dark matter fluid in the universe and none of the baryons. And that means we actually only need to follow gravity in an expanding background of space-time. And so here's an example of one of these simulations. This is from Volker Springel's group. It's the Aquarius simulation. In this particular simulation, it's modeling a patch of the universe that's going to come together and form a blob of dark matter about the mass and size that we think hosts our own Milky Way galaxy. And in this particular simulation, Volker's assumed that dark matter is perfectly cold, so purely non-relativistic, and that it's perfectly collisionless. So it really only interacts via gravity. And that's what leads to this cosmic web structure here, that the dark matter collapses along the shortest axis first to form pancakes. Where those pancakes intercept one another, you get these filaments, and where three pancakes intersect, you get these nodes. And it's at these nodes, which we call halos, where we think gas will cool and stars will form, and we'll have little galaxies, okay? Now, we can extract an awful lot of information from a simulation like this that we can then go and compare with the real universe to test dark matter models. So here's this cold dark matter case. Now, because dark matter is cold and collisionless, you see it collapsing on every scale down to the resolution limit of the simulation. So you see these very tiny little halos all the way all over the place here. If we swap this out for one of these warm dark matter models, then there's a lot less power on small scales, and that manifests in many fewer halos. So this is a 1.5 keV thermal relic, and you can see visibly how much smoother this simulation is. And if every single one of these blobs hosted a visible galaxy, then I could distinguish between these two models simply by counting the number of galaxies in some well-defined patch of the sky, okay? And that's basically how the galaxy count method works. But you can already probably see there's a complication here because I have to understand how stars inhabit these dark matter halos. We'll come to that in a minute. Now, the second thing you can get from this sort of simulation is you can actually extract the internal structure of these dark matter halos, like this one here. And it turns out, and this is a result that goes all the way back to Navarro, Frank, and White in the 1990s, that for the cold dark matter simulations, at any rate, all of these halos have what we call a self-similar dark matter profile. And this is called the Navarro, Frank, White profile. And it's basically a split power law. They go as a steep r to the -1, what we call cusp, because this diverges towards the origin. There's some sort of break radius, and then they fall off as more steeply as about r to the -3. And that's the prediction for a cold dark matter cosmology. In a warm dark matter cosmology, you actually get the same shape, but all the halos are substantially less dense. But you can make further changes too. So there is a whole class of model called self-interacting dark matter, where you introduce an extra force in the dark sector. And when you do that, you allow the dark matter particles to exchange energy with one another much more efficiently than they can through gravity alone. And so that causes this cusp to go away and collapse into a much lower density core. So this is a self-interacting dark matter model with about 1 centimeter squared per gram cross-section. And so you can test the difference between these different models, not by counting galaxies, but by measuring the dark matter distribution inside galaxies and trying to map out where the dark matter is and see which of these models is best. So these are some of the kinds of things we can do to probe the nature of dark matter just using gravity. Now, these pure dark matter simulations, I would argue, are pretty well understood. Okay, this is a nice study from Aurel Schneider from a few years ago, showing the power spectrum, in fact, at some different redshifts, redshift 0 being today, of course, run with different numerical software packages, Ramses, Gadget 3, pkggrav. And you can see that on large scales, they all agree to much better than 1%. But even as we approach these nonlinear scales, these calculations agree at better than 4 to 5% accuracy. Interestingly, with Euclid coming and large new satellite surveys and so on, this probably still isn't accurate enough, believe it or not. But it's still pretty impressive for the kind of probes that I'll be talking about. This is far from the dominant source of uncertainty. So I think we can say that the pure dark matter calculations, accurate to 5% or so, are very solid. And the same is true for the dark matter halo structure. This is a study from a few years ago, Joachim Stadel from the Zurich group, of convergent study. As you go up in resolution, this is what the dark matter density as a function of radius looks like, and you see this very cuspy, steep density profile consistently emerging. As you go up in resolution, you get a lovely converged result. So that's the good news, right? That if the universe contained only dark matter, the calculations would be actually quite straightforward and robust. The bad news is that the universe doesn't only contain dark matter. I mean, if it did, I couldn't be here giving you this talk today. So we do need to add the one bit of the universe that we actually know exists, which is all the baryons. And there's a couple of reasons why that's really important. And the first reason is just we don't tend to see this dark matter universe. We can try to infer it through gravitational lensing or dynamics or whatever. If we just look up at the universe, what we see is starlight. If you want to count galaxies, for example, to test dark matter models, we need to know how stars and gas inhabit all of these dark matter blobs. So here's an example from the Apostle simulation collaboration from Til Sawala and Azi Fatahi, where this is the underlying dark matter in their calculation, but in their calculation, they've included a model for gas cooling and star formation. And if you look at what this looks like in visible light, then it actually looks like this. And you see the two main galaxies inhabiting the two main dark matter blobs, and a few of the other more massive blobs have stars, and the rest of it is all dark. So you see an awful lot of structure here, like this little blob, just not there in visible light at all, okay? And so if you want to count galaxies and figure out what dark matter is, you've got to get that right. Which halos light up in stars? Can we calculate that robustly enough that we can derive confident constraints? And the second problem, which is actually even a bit more tricky again, is there's growing evidence, and I'll show you some of this in a minute, that dark matter could actually be physically rearranged during galaxy formation, particularly at the centers of dwarf galaxies, but actually it can be impacted on all scales. And the reason for this is, even though dark matter makes up most of the mass of the whole universe, once you zoom down to the very center of one of these little galaxies, the dark matter, at least in pure cold dark matter models, it's very difficult for it to lose energy, to dissipate, because it only interacts via gravity. So when a dark matter particle picks up kinetic energy as it falls into a potential well, it's kind of stuck with that energy it gets after the halo, what we call virializes. Whereas gas can shock, emit photons, and cool down, collect at the very centers of dark matter halos and form stars. And when it does that, it can actually dominate the gravitational potential right down at the center. And if it's dominating the gravitational potential, it can actually, just via gravity, pull the dark matter particles around and actually alter the inner structure of dark matter halos. Okay, so those are the reasons why we need to include baryons, but let me just spend a minute explaining why it's so difficult to include baryons and why there's still some debate about what the right answers are when we do the calculations. So here's another one of these simulations, this time from the illustrious group, just trying to give a fair coverage of all the great stuff that's going on there in the literature. This is another one of these large volume simulations with stars and gas. So this is the visible light from this large patch of the universe, about 50 megaparsec cube volume. And then I've painted on here an actual image of a real little dwarf galaxy that lives out in a void. And let's zoom in on that. So this is 50 megaparsec cube, and this is the kind of volume that we need to model if we want to get the tidal field of one of these little galaxies about right. So we need our whole simulation volume to be at least this sort of size. And here's the kind of galaxy that we want to try to numerically resolve in that volume. This is the M82 dwarf galaxy. This is now a real picture of a real galaxy. It's a composite image. So in white here we see stars. This dark stuff is dust in the disk of this galaxy. But what I really want to draw your attention to is this gaseous outflow in purple here. This is hydrogen gas that's being blasted off in a huge galaxy wind from this galaxy. And the size scale is now about 2 kiloparsecs. So very, very, very much smaller scales. Now, these winds that are being blasted off, these are key to regulating galaxies. They're like a natural galactic thermostat, that when stars form, the massive ones, they explode, and the effect of many such stellar explosions overlapping with one another, we believe, drives these galaxy winds, and that regulates the further formation of more stars. And this is an absolutely key process to get right, to figure out how efficiently galaxies form stars, but also to figure out whether or not this inner dark matter gets messed about. And to get those winds right, that means, of course, we need to actually resolve even smaller scales where the stars form, where the stars explode, because that's the physics that's driving the formation of that wind. And that occurs on even smaller scales. This is now 250 parsecs. And this is a real image of a star-forming region in the nearby Large Magellanic Cloud called 30 Doradus. And again, it's a composite image. These red blobs here are now hot X-ray gas bubbles. And the energy of each of these bubbles is the sum of many supernova explosions, so hundreds of supernovae. And these bubbles get driven by that stellar feedback. And when they overlap, from this star-forming region with others around the galactic disk, that's what ultimately drives the galactic wind. So if we want to get the baryonic physics right, we really need to be better, substantially better than 250 parsec spatial resolution. We need to resolve this multi-phase gas. We need to get these hot bubbles to come out as an emergent phenomenon, their overlap driving galactic winds. That should all come out of the calculation naturally. Okay, that sounds terrifying, perhaps, but the good news is we can actually do calculations with that kind of dynamic range in space and time now. And the reason we can do it is using a trick called cosmological zooming, or zoom simulations. Here's an example from just a pure dark matter simulation from Wang et al. What you do is you take your big volume of the universe that you need to get the tidal fields right. You then select a region of interest, say a single galaxy, and you have this large region at rather coarse resolution. And then here you put more resolution, which is now this circle. And then you zoom in again on this bit here, you put more resolution, and you can just keep on going until you resolve the very small structure that you want to actually capture. So one single little galaxy in the context of that large volume. And when you do that, you can then actually get down to these kinds of resolutions, 25 parsec or so, over this enormous volume. So let me show you what one of these sorts of simulations looks like. This is the Wintergatan simulation. This is the state-of-the-art simulation now of the formation of our galaxy, the Milky Way. And what you're seeing now is the gas temperature in this simulation. This is from Aguirre et al. So it's rather similar to the Aquarius simulation I showed you before, but now instead of looking at the dark matter, there is dark matter here, we're just looking at the gas. And you can see all these hot gas bubbles forming, and these are driven by exactly those supernovae. So you can see all over the place, there are little galaxies here behaving like M82, all right? Now, already at high redshift here, this is a nice point to stop for a second, just to illustrate how this is important, even for the Lyman alpha constraints. Right? The Lyman alpha constraints, remember, we got that photon from that quasar traveling through the whole universe towards us, piercing all that hydrogen gas. Now it's neutral hydrogen that photon pierces through. So if the hydrogen gets heated up by these galaxy winds, then that will actually change the forest of absorption lines. So that creates a degeneracy between the forest of absorption lines and the thermal history of the universe that depends on all these baryon physics. So even the Lyman alpha forest, especially now that we start to probe these much smaller scales, is impacted by the quality of these numerical simulations. All right, let's take the calculation further forwards again. You can see, rather like before, only some of these galaxies are going to light up in stars and gas. Some of them, just like this one here, will gradually fade away as it gets blasted by gas from other nearby ones. And you can see that these galaxies are affected both by the internal processes inside, from their own stars, but also from all the surrounding things that are going on. And you can see in a calculation like this now, as we start to approach redshift 0, the gas starts to collect in a nice rotating gaseous disk. About redshift 1, the major mergers will be over, and we'll start to form something that looks a little bit more like your sort of canonical image of a nice disk galaxy. And that sort of thing is now actually emerging naturally from these sorts of calculations. The spatial resolution of this particular simulation is now at about 20 parsecs. So it's really starting to approach the kind of resolution that I was saying before that we need to pass that next hurdle of realism. Okay. Okay, so how are we doing with these simulations? Well, we can go and compare them to real galaxies and then sort of estimate how well we're getting on. And there's many ways we can compare. We can compare the metal content of these galaxies, their sizes, their shapes, all the rest of it. But let me pick an extremely simple metric just to start with, which is just the total number of stars as a function of the total mass in dark matter. Okay, so here's the dark matter halo mass on the x-axis and the stellar mass on the y-axis. And these purple points, this is all real data, where the stellar mass is estimated from the photons of light coming from the galaxy, and the halo mass is estimated from the dynamics of the rotation of the gas disk. Okay, and this is a compilation of data from CATS and from a paper I wrote a few years ago. And you can see that they follow quite a nice trend, that basically the stellar mass and halo mass are quite well correlated. But these blue points here, these are Zoom simulations, recent Zoom simulations from the FIRE collaboration. The Vindicatin simulation sits about here. I should have marked that on the plot as well, and it sits very nicely. But the FIRE team have run quite a few of these at that sort of resolution. And you can see the agreement is starting to be very good, that they're recovering the trend and they're beginning to recover the scatter. Of course, the flip side with these kinds of very high resolution simulations is you can only afford to run a handful of them. Vindicatin took about 6 months to run just that one simulation on like international supercomputer resources. So you can't run too many of these things, but to the extent we can, we really do seem to be matching the data. Where things start to go wrong, though, is down here at the scale of the smallest galaxies. And that's a slight shame because it's on these very small scales, remember. This is where all the information about dark matter is encoded, right? This is the bit we really, really need to get right, and it's not clear that we are. First of all, there's not much data down here. There's 2 data points for galaxies down here, so that's not a great situation to be in. And secondly, simulations from different groups actually disagree quite violently on what should be happening down here. Farah Munshi's work with Alison Brooks is in orange here, and my own simulations are in black. We agree with each other, but the FIRE team form many fewer stars per dark matter halo mass. And this really matters because if I go and count galaxies, for example, that have 10 to the 6 stars, right? The fire team would say that those galaxies live in these 10 to the 10 halos, whereas the Feramunci and me would say, oh no, it's more like, 5 10 to the 9 or 10 to the 9. And so we would get very different inferences about the nature of dark matter based on those two different assumptions. So this is really the battleground. This is where we need to start getting things right. And right at the end of the talk, if I have time, I'll talk about some recent progress down here where I think actually there is hope that we can get this right. Okay, and the last thing I mentioned before is that, all of this gas getting blasted out and cooling and flowing in and flowing out actually causes the central gravitational potential to fluctuate with time, right? And that can actually affect the distribution of dark matter at the center of galaxies. And I want to just show you roughly how that works. This is a process that has become known over the last few years as dark matter heating. It's really kinematic heating. Obviously, cold dark matter doesn't have a temperature or pressure to speak of, really. So it's a kind of a kinematic heating. It just means pumping energy into the orbits of the dark matter particles. And so how can that happen? There's no exotic dark matter model here. This is just for standard, Susie WIMP, if you like. But what will happen is that when the gas cools, the gravitational potential gets a little stronger. And when it gets blasted out in a wind, the gravitational potential gets a little bit weaker. So you get this fluctuating gravitational potential as a function of time. And it's not a huge effect, right? It's fluctuating by maybe 10, 20%. But I'm going to show you that's enough to actually quite significantly alter the inner structure of dark matter halos. So to show you that, this is a simple toy model where I'm going to have a single dark matter particle moving on a nice circular orbit in a little dwarf galaxy. So it's a 10 to the 10 solar mass dwarf galaxy. And then I'm just going to wiggle its gas to dark matter mass ratio up and down to mimic this gas cooling and being blasted out. And I'm going to wiggle it up and down by about 10 to 20%, which is about what we see in the simulations I just showed you before. So here we go. So to begin with, for the first billion years, I'm not going to do any wiggling. So we get a nice circular orbit. That just proves I can integrate a circle. And then now we start wiggling up and down. And this kind of stochastic wiggling is very similar to what we see in the actual full simulations. And this creates a time-varying gravitational potential that pumps energy into the orbit of the dark matter particle, causing it to slowly migrate outwards. The same would happen to the orbit of the Earth around the sun. If I just wiggled the mass of the sun up and down, it would be kind of bad for life, so I'm not going to do that. But you can see this dark matter particle gradually migrating further out. And if you imagine this happening to every dark matter particle in the middle of the galaxy, then the whole halo will slowly expand. And that actually causes this steep density cusp to get less steep and get pushed down towards something much flatter, more like a dark matter core. So this is what that looks like. This is from a calculation we did a few years ago. You start off with a steep dark matter cusp like this. You have this repeated gas inflow outflow as stars form, as gas cools, as gas is blasted out again. And the dark matter halo is gradually transformed from something initially cuspy over many billion years of this gravitational potential fluctuations. The dark matter halo is pushed down towards something much flatter and much more core-like. And this effect is really important because if you remember back a few slides ago, I argued that this red line here is the prediction for self-interacting dark matter, right? So if I go out and measure the dark matter distribution in these dwarf galaxies and I see the red line, I might be leaping up and down and going, dark matter must be self-interacting. But in fact, that may not be what's going on. It could well be, in fact, that it's this process. And in fact, it turns out that since the 90s, dwarf galaxies have favored this red line over the black line, and that's become known as the cusp core problem because this is cuspy and this is chord, and it's generated loads of interest in the literature. But my personal feeling is that it is probably just due to these baryonic processes that were very hard to model, that we didn't resolve in the previous generations of simulations, and that we're beginning to resolve now. And the reason why I'm sort of starting to get more confident about that statement is because this model made a prediction, right? All good models should make a prediction that you can then go and test with real data. And this model did exactly that, because if you look at the timescales here, right, it takes many billions of years for this profile to change from cuspy to chord. It doesn't happen overnight. It can't happen overnight because you've got to wiggle the potential. You're not doing it. You're only doing it up and down by a few percent. It's a tremendously inefficient process, so it has to take time. But what that means is if you can find a sample of galaxies that all inhabit similar dark matter halos, but had different amounts of star formation, then you would expect the ones with hardly any star formation to be closer to this black line, because they haven't had the star formation, they haven't wiggled their potential, they should be closer to the pristine dark matter solution, whereas the ones that have formed stars for many billions of years should be closer to the red line. And a couple of years ago, we gathered together a sample of data for galaxies that met those criteria, and timing was everything. We finally have enough galaxies with enough good data we could do this. So we gathered together a whole bunch of dwarf galaxies that inhabit similar halo masses, but some have formed lots of stars, some have formed very few stars, and we put them all on one plot, and this is what we found. So this is the inner dark matter density, right down near the center of the dwarf galaxy, as a function of the stellar to halo mass ratio. And as m star goes to 0, of course, we're forming no stars. And you can see that these systems, obviously the error bars are quite large, but they are systematically denser and actually much closer to that pristine dark matter prediction. And as we form more and more stars per unit halo mass, the dark matter density is systematically lower as we go over here to these systems on the right. And a few years ago, Arianna Di Tintio predicted where systems would start to be sort of cuspy versus chord, and she predicted the transition should occur around about here where this dashed line is, and that's in really nice agreement with these data and with this anti-correlation. So I think there's mounting evidence. I mean, this plot is still heavily debated, I should say, and I'm happy to talk about it in questions. But I think most people are now happy that the data are correct. So now we're just fighting about the interpretation. But this anti-correlation was predicted by those dark matter heating models, and it does seem, to my mind, to have been observed. Okay, so just to recap where we got to so far, pure dark matter simulations are well understood. When we add baryons, it's important because we need to know which halos light up in stars, and it's important because baryons actually seem to move dark matter around at the centers of galaxies, and we need to get that right if we want to make inferences about the nature of dark matter from those kinds of observations. So I'm going to switch gears now and actually talk about what kind of constraints we can really get from the power spectrum on very small scales, and I'll highlight successes and I'll highlight some challenges referring back to the challenge of the simulations that I just spoke about before. So as I mentioned before, there's three main probes on very small scales that I think are the most competitive at the moment: galaxy counts, lensing, and stream bumps. So galaxy counts is probably the easiest one to understand. That's the one I've referred to several times already. If I can figure out how stars inhabit dark matter halos, then I can just go and count galaxies in a nearby volume and infer which dark matter model that's most consistent with and which dark matter models are out, they don't work, right? And people have been doing this for a while now. We can now count satellite galaxies, for example, around our own galaxy, the Milky Way, and around a whole bunch of nearby Milky Way analogs. So this is from Carlson et al. Just from last year. And this is the Milky Way. Here's the nearby Andromeda galaxy, and here's several other Milky Way analogs. The data are in red, and the data show the cumulative number of galaxies above a particular brightness. We call that the V-band magnitude as astronomers, but it's just some brightness as a function of that brightness on a logarithmic scale. Okay, and so you see there's more faint galaxies than bright galaxies, and this line sort of cumulatively rises to the left. And the prediction for pure cold dark matter with 68%, 95% confidence is shown here. And you'll see that the predictions are quite broad, and that's because the LCDM theory, right, structure formation is quite stochastic, so you get an enormous amount of scatter in the expected number of galaxies for each Milky Way. So you're going to need lots and lots of these galaxies to really pin down the model. But for the time being, the data are perfectly consistent with, or LCDM, if you like, is perfectly consistent with the data. Now, so this is a success for the model so far, but of course, this brightness of -10 or so, these are still quite massive dwarf galaxies. And if we really want to test the nature of dark matter, we actually need to do this model data comparison much further over here on the left, okay? And you can start to see some hint of that already, that all of these theory predictions are rising very steeply off the left edge of these plots, right? And so unless this red line also goes up very steeply, you can see that not too far left of here, the model and the data are going to start to be discrepant, okay? So we want to do these kind of comparisons at much, much lower mass for the very, very faintest systems in the universe. But to do that, we need to get this mapping right down here, where it's still all a bit uncertain, okay? So the latest constraints range from 2 to 6.5 keV thermal relic, and that range really comes down to fights about, you know, how stars map to dark matter halos and which of these curves is the correct one. And if I have time right at the end, I'll talk about how we're making progress here and how I think we can actually move forwards. But for the moment, there's this huge error bar here, which is entirely a theory error bar based on this uncertain mapping. Okay, the second probe I wanted to talk about is stream bumps. And the way this works is if you imagine a little star cluster like this falling into a disk galaxy like this, as it falls in, its stars gets tidally torn off in what we call tidal tails. And you can see one tidal tail moving off this way and the other one moving off that way. And these tidal tails are quite smooth. You can see in this simulation here, they're really smooth. But if I filled this galaxy with lots of these dark matter lumps, like you saw in the movie from before, then those lumps move around and they'll hit this stellar stream, and they'll actually create like granularity and substructure in the stream, little holes, little bumps and wiggles. And so we can then use the statistics of those bumps and wiggles to try and infer the granularity of the underlying dark matter halo, and thereby how cold dark matter is, okay? And so this is not just an idea anymore, it's actually an industry. It's actually coming along very nicely. One of the people at the forefront of that is Dennis Erkal, who's also at the University of Surrey with me. This is some beautiful work from him and his collaborators on the PAL5 stellar stream. Here you see a numerical model of the PAL5 stream. PAL5 is a little star cluster here, and it has 2 stellar streams coming off here and here. And here, Dennis has tried to fit a model to this stream. And if the model assumes that there's no dark matter substructure at all, it's all perfectly smooth, you just can't fit the stream at all, right? Here's the density or the over density, and you can see the stream wiggles, got all these bumps and wiggles in the real data that are simply not there in the model. But if he adds to the model just a couple of dark matter blobs, one with 10 to the 6 solar masses, one with 10 to the 7, then he can actually start to reproduce all these wiggles really beautifully. And if you remember right back to the start, when I showed the power spectrum, along the top, I marked the halo masses. And you may remember that 10 to the 6 solar masses, that's really probing very, very far over onto the right into the nonlinear regime. If this turned out to be a definite dark matter lump at 10 to the 6 solar masses, we'd be really pushing 10 keV like constraints on warm dark matter, so hugely competitive, okay? However, the problem is that anything that hits that stellar stream will create a lump and a bump. And this was shown quite nicely by Amerisco, where you see, again, a nice simulation. This is a smooth stellar stream with no substructure. And here you see one all lumpy. But these lumps down here have been caused just by gas clouds. Okay, gas clouds can also have masses of 10 to the 6 to 10 to the 7 solar masses. Plenty of them live near the disk of our galaxy. And these can produce similar effects without any need to invoke dark matter at all. So there are constraints in the literature now already from Bannock et al. Pushing 4 to 5 keV at 95% confidence. But for this to really become robust, we've really got to understand a whole bunch of complicated physics. You know, what is the effect of gas clouds? What's the effect of known star clusters? The bar of the Milky Way can have a role. So there's a lot of work still to be done to really shore this up, but the method certainly holds a lot of promise. Okay, and the third technique that I think is very sensitive is strong lensing, and here's some lovely work from Simona Vighetti. You know, you may think, how on earth does a little dark matter blob that's only 10 to the 6 or 10 to the 7 solar masses produce any appreciable gravitational lensing? Well, and you'd be right. But the trick here is you find an absolutely whopping galaxy cluster, something that's already producing a tremendous amount of lensing and that has a beautiful thin arc. This one here seen in radio using very long baseline interferometry. And then what you do is you hope that along this thin lensing arc that's being produced by this enormous galaxy cluster, 10 to the 14, 10 to the 15 solar masses, that somewhere along here, you have a tiny little dark matter blob along the line of sight. And then you get this little bit of extra lensing you can see here from the zoomed in panel. You see it here for 10 to the 7, you see it here very clearly for 10 to the 8. You can detect it here statistically even for 10 to the 6, okay? And again, then it's a game of statistics. You want to find as many of these arcs as you can, and then just figure out if this thing is really cold dark matter and there's all these blobs everywhere, you know, what's the probability that absolutely none of them lie along this arc? And the more arcs you find, the lower that probability is, and eventually you can infer also the nature of dark matter. And these constraints are now also pushing sort of 5 keV. So while each one of these probes has its problems that I hope I've spelled out quite clearly, the fact that all of them are really starting to push on 5 to 6 keV suggests that may well in fact be the case, and that dark matter really is, if it's a thermal relic at all, it's certainly more massive than about 5 keV or so. But again, lots of complications here to be really worked out. All right, in the last 5 minutes or so, I'm hoping I've still got 5 minutes or so. I just want to say a couple of words about the future. And you know, the lensing constraints and the stream bump constraints are really beautiful. They're beautiful also because they directly probe the dark matter, right, rather than the visible components associated with the dark matter. But they're also quite complicated to get the modeling right. And probably the simplest probe is galaxy counts, but the big problem with galaxy counts is, of course, getting that mapping from light to dark right. So what we're trying to do in my group at the moment is really make that completely robust, try and really pin down the galaxy halo connection in these smallest galaxies, so that we can use galaxy counts as a robust probe of the nature of dark matter. And that's what we're trying to do in what we're calling the EDGE project. This is engineering dwarf galaxies at galaxy formation's edge. And what we've done here is we've taken a void volume of the universe now, so a very low density patch of the universe. And the reason we've done this is so that we can use the zoom technique I spoke about before to zoom in on really tiny galaxies in this volume, and then get to really, really high resolution. So we're getting to sort of 3 parsec resolution here, you know, baryonic mass resolution of 20 solar masses or so. And at these sorts of resolutions, we actually are forming individual stars, or individual massive stars anyway, and we're capturing the effect of individual supernova explosions on the surrounding ISM. So we pass another level of realism as compared to the calculation I showed you before. And what's quite nice about that is when we do this, without any fine-tuning or fiddling of numerical parameters, we seem to be forming very, very realistic looking galaxies. So here's, these are all data points for real galaxies. This is showing you the stellar velocity dispersion, which is basically the relative velocities of stars in these galaxies versus their size. And this is showing their brightness versus their size. But the key point here is that in all of these data plots, marked on top are these black dots, and these are our EDGE simulations. You can see that they're inhabiting the right sort of space and scatter of the real data without any fine-tuning. So what we can now do is we can take those EDGE simulations and we can say, well, what do they predict for the stellar mass halo mass relation, for the star dark matter connection? Now here's the data I showed you before. I'm just focusing on the low mass data now in purple. This is this abundance matching line from Baruzzi. And here are the actual simulation points on here. And immediately you see that once we get down into this regime, one of the reasons why all these simulations may have been disagreeing with one another is because there's actually an enormous amount of scatter in the stellar mass to halo mass relation. And you see this stripe here, right? This is actually a nice feature of our EDGE simulations, because one of the cute things we can do, this is some lovely stuff that Andrew Ponson developed, is we can take a halo in the early universe and we can actually engineer it so that it forms a little bit earlier or a little bit later, the exact same halo. And that means we can actually do sort of numerical experiments in this full cosmological setting. So here we took this halo with this mass and we just made it form earlier or later. And this halo is so small that when all the stars in the universe switch on, the photons from those stars ionize all of the hydrogen gas, and they cause star formation to shut down in a process that we call reionization. And because that happens at a fixed moment, a fixed epoch in the age of the universe, if this halo forms earlier, then it can form a lot more stars before that epoch comes along and shuts star formation down. But if it forms too close to this epoch, then it will form hardly any stars. And that's what you're seeing happen here. This up here formed really early, got lots of star formation in before reionization. Down here, it formed too late, didn't form enough stars before reionization. And you see the same thing happening up here. And it's only when you get up to about this sort of 10 to the 10 solar mass scale, these halos are so massive that they don't care about reionization anymore. Those ionizing photons can come along, and they're now big enough that they can just keep on forming stars anyway. So you get lots of scatter down here, and then less and less scatter, and then up here you start to get almost no scatter. So that's the picture, but you can see already there's still an issue, right? The data points are up here, the simulations are down there. They don't really seem to be agreeing with each other. And what's worse is that we can't really do statistics, right? These are all the simulations that we've run over 3 years, right? Each one of these simulation dots takes many months to run. This is 3 years worth of work just to have this smattering of points, which is not a statistically representative sample of galaxies in the universe. So to try and deal with that problem, we've got a wonderful postdoc working with us, Stacey Kim, and she's developed a new tool called Darklight that has learned how EDGE paints stars onto dark matter halos. I won't go too much into the detail of how it works, but it's all based on this really beautiful plot where we find a nice and tight correlation between the mean star formation rate of galaxies and their masses, using this measure here as a proxy for their mass. And these tight correlations are basically the secret sauce that goes into dark light. That's all that goes in. And what comes out is this. So this is showing the growth in stellar mass as a function of time of one of our full EDGE simulations that took months to run, these black lines, and Stacey's dark light calculation that runs in seconds and reproduces the same answers, right, including the little steps and everything. So the beauty with this now is dark light takes seconds to run. It's learned how EDGE works, but it runs much faster. We can now run it on large volumes. Okay, so we can take dark light, go back, run it on every halo in that void volume I showed you a minute ago. And what do we get? We get this. Okay, so we can now predict the stellar mass halo mass connection, but for now for a statistically correct sample of galaxies. And now suddenly we do start to form points up here, albeit rarely. You can see there's more scatter even than we got from EDGE alone. And the calculation predicts now not only the relationship between stellar mass and halo mass, but it actually predicts this scatter. And if you change the cosmological model, the scatter may well change too, and it will predict that too. So this is giving us now what I think or hope is a firm foundation on which we can now go and do robust tests of dark matter models all the way down here in these very small dark matter halos. And I think that will allow us with the next generation of surveys like LSST, the Vera Rubin Observatory. This will really allow us to start to push that kind of 10 keV limit in a robust and secure way. All right, so I'll leave it there. I know that's quite a lot of stuff for one talk, so I hope you've kept with me all the way. I'd say the latest constraints on thermal relic dark matter from Lyman alpha forest, strong lensing, galaxy count, stream bumps, they all point to dark matter being rather cold, at least 2 keV, probably more than 5 or 6 keV. There are challenges for each of those probes, and they're all wrapped up in trying to model the universe on small scales, including baryonic effects. And a key uncertainty is how stars inhabit the very smallest dark matter halos. But we think we can now make progress by running a small number of very, very high resolution simulations, and then using another tool to learn how those simulations work so that we can ratchet up some good statistics from those simulations. That's work now sort of largely in hand. So I think over the next few years, sort of watch this space, I think we'll be able to push at least the galaxy count method towards very tight constraints on the thermal relic temperature of dark matter, and to push for other constraints on things like self-interacting dark matter as well. So that's all coming soon, and I think that's pretty much where we are. So I'll stop there for questions. Thank you.
Thank you very much for the great presentation. Very nice. Thank you. Are there any questions? I don't see any. I have a no. Mark Richardson was first.
Cool. Yeah, thanks, Justin. That was a great talk. I'm curious a little bit about the feedback processes that you have in Edge. Yeah, I'm wondering if you could just say a couple words about that, and I guess how that was decided, because obviously you're showing that your galaxies are completely consistent with those observed. So I'm assuming this is a result of some tuning in your feedback.
Yes, so that's a really good question. So actually it's not a result of tuning in the feedback. Now there's a couple of things, right? First of all, with Edge, we're reaching a spatial and mass resolution where we actually capture the formation of small molecular clouds, right? And these are the regions where in the universe we can see stars actually forming. So to the extent, you know, our default numbers that we put in for like the rate at which gas is turned into stars and the energy from supernova explosions all comes from what we think we understand about stars. So we put in what we think we know about stars. It's not obvious that you then get galaxies to come out right, but we kind of do. But in the first Edge paper, we took one galaxy and we just changed all the knobs and dials to see what would happen. And the interesting thing is you can dial the star formation rate up and down by factors of 10. And the galaxies still broadly come out looking about right. And the reason is because the feedback acts as a kind of natural galactic thermostat, that if you form stars 10 times faster, you get 10 times more feedback that then self-regulates the star formation. Now, but there is one thing that cares, which is the stellar mass metallicity relation. So if you dial up the feedback too strong, you start chucking metals out the galaxy too quickly, and the galaxy ends up being far more metal poor than real dwarf galaxies, and vice versa. If you dial down the supernova too much, then the metals don't escape and it self-enriches and everything ends up, you know, approaching solar metallicity. So what's really interesting is if we put in the numbers that we just, you know, would have guessed from what we think we know about star formation, the stellar mass metallicity relation comes out just right as well. And when we overpower the supernova, we end up being wrong. Okay, and when we underpower the supernova, we end up being wrong. So it's starting to feel like, you know, now that's not to say that we've got every bit of physics that one could write down in there. We haven't done, you know, there's no magnetic fields. There are stellar winds, supernova feedback. We've done explicit radiative transfer. And that does make a difference as well, but of a sort of next to leading order kind of difference. But there's other physics in there that could go in there as well. So either all the other physics that we haven't got in there, like magnetic fields, is next to leading order, or it conspires to cancel itself out somehow. And this is stuff that we're beginning to work on now in sort of Edge 2.0. But yeah, but we can't afford to do too much fine tuning because each simulation takes months. So yeah.
It's like Zoom, let me unmute. Yeah, thanks a lot. That's great.
Sure.
Tom, you're next.
Okay. In your Zoom simulations, you're feeding information from the larger scales down to the smaller scales. How much information do you have to feed back from the smaller scales to the larger scales?
Yeah, so that's an excellent question. So there's two ways in which the scales interconnect. Obviously, they interconnect through gravity, and there it's much more large scales on small scales than small scales on large scales. Where the small scales, like talk with the larger scales more intimately is through these kinds of feedback effects. And that's why that's actually why all of this is so hard, because the stellar feedback is being generated on sort of parsec sort of scales from where stars actually form. But if you remember back to the movies, those or even the data, right? Remember M82, the gas coming off the galaxy is impacting the intergalactic medium on tens, 20 parts. So information that's generated in the very smallest parts of the simulation is feeding back and talking to much larger scales in the simulation. So it really matters that we get that right. But in terms of actual like numerical communication, the astrophysics is all local, right? You just talk to your next cell, and then it talks to its next cell, and it talks to its next cell, and so on. So I don't know if that quite answers your question, but
Yeah, I think that makes sense. Thanks.
Lawrence, you're next.
Hi, Justin. Thanks for the talk. Related question, are there any dangers in pushing Zoom simulations too far and going, is there any limit as to just how far you can go? Getting the gravity wrong of too many large particles leaking into these smaller and smaller boxes.
Yeah, that's an excellent question, and good to hear from you as well, by the way. Hello. Yes, absolutely. I mean, there's some really heroic stuff in the literature with like 42 levels of refinement. That isn't the case here, right? I mean, these are not what I would call aggressive zooms. We have maybe 3-4 levels of refinement, and we also, before we populate any of the dwarf galaxies with stars and gas or anything, we do a contamination check. So we carve out a pretty large Lagrangian volume around each dwarf, and we make sure that there's no zero low resolution particles that enter that volume. And so that's a sort of a slightly fiddly aspect to the calculation, where we do still have to do a little bit of manual checking and pruning before we do our production runs to make sure that there's none of this contamination, because I worry about exactly the same thing, right? If you have a low resolution dark matter particle plow through the middle of your dwarf galaxy, it's like throwing a giant black hole at it or something, which is not what you want. Yeah.
Okay, thanks.
And next question is from Stefan.
Hello, Justin.
Hi.
It's been a while. I had a similar question as Larry's, and in a way I had a similar question as Mark. So I'm going to try to combine them, in fact, and ask you, because there's a limit again to how small a resolution we can achieve. So combining these two questions would be: do you predict Kennicutt-Schmidt, or must you hardwire Kennicutt-Schmidt in your simulation?
So in these, so to be honest, I haven't looked. We will look at Kennicutt-Schmidt in sort of what we call Edge 2.0, but I haven't so much looked at it here because the galaxies we're modeling are so small that they don't even have well-defined disks. But I've got some simulations that are running now that are not published yet. We're beginning to form disks. Certainly in the Milky Way mass one that I showed you, that's not as high resolution as Edge, right? That one forms a disk, and the Kennicutt-Schmidt relation emerges in that simulation, right? And I'm hoping that the same thing will happen in Edge. So we put in like a Schmidt law locally for star formation. Mm-hmm. So we form stars on a gas free fall time, but as you know, that's not quite the same as the Kennicutt-Schmidt law, which is so the Kennicutt-Schmidt surface density law comes out, but you put in the local 3D Schmidt law, right?
Sylvia, can I make one more comment? Just sure. Perhaps Justin must appreciate that we're very proud and pleased to welcome Surrey people here at Queen's University. We have, I don't know if you know, we have 2 of your former students here, Lucy Sampson and Charlie O'Sullivan are with us. They have taken your classes. They're working with me and Joe Pramonte. And I was wondering if Charlie and Lucy could just pop their camera very quickly to say a big thank you to their former professor, and perhaps just tell you very, very quickly, unless Sylvia objects, about their project. Lucy?
Yeah, I'd love that, yeah.
Hi. So I'm working with Joe, and my project is looking at how dark matter induced supernova affects galaxy formation, so feedback. So kind of some of the stuff you were saying before about the bubbles and the gas outflows and stuff. Yeah, that's what I'm working on.
Excellent.
Hi, Justin. Great talk, by the way. Yeah, I'm working with Stefan as well, and we're looking into galaxy properties and investigating further certain bimodalities seen in certain properties. So yeah.
Cool. Yeah.
Just wanted to keep it quick, but and also saying hi to you, Justin. It's been a long time since Zurich.
No, I know. It's great to see everyone, actually. And I mean, this is the positive and negatives of Zoom, right? You get to catch up with people all over the world, but then you never quite get to catch up I've still been marveling at seeing people in 3D. You know, like I walk around behind them, I'm like, oh, I can do that now. But it's also great to see our science students doing well. That's really good. And I hope they and you are pleased with the preparation that we put them through.
Very much. No, seriously, and not exaggerating. We're very blessed to have Charlie and Lucy working with us this summer. Anyway, I won't take up too much of this time. Thank you very much. Good seeing you again, hopefully in 3D, 4D coming soon.
Yeah, absolutely. 4D, I like the sound of that.
Thank you very much, Stefan, and welcome, Charlie and Lucy. And Mark, I see
And
your
maybe,
hand up. Sorry.
yeah, I have I don't know, maybe a little bit of a technical question, but I know that when you do the variation with the genetic algorithm from Andrew Ponson, you do have a sense of really like how unlikely is the change that you made. And so I was curious, the variations you were seeing that gave you such a variation in the formation time, which effectively changed your M star for a given M200. How rare were those changes you were making to the initial conditions compared to, I guess, like the underlying scatter that the dark light models were predicting? I guess I was trying to like get a sense of like from the initial conditions, how rare are the changes you're making compared to how rare the output you're getting in the scatter?
Yeah, so I mean that's really interesting because so when we do the GMs, we tend to pick them from within the 1 to 2 sigma contours of the background population from the pure dark matter simulation, right? So they shouldn't be too rare, but it's not an exact science, right? And what's interesting is now with dark light, we can kind of go back and check that after the fact. So you can see here, this stripe should have been within the 1 to 2 sigma scatter. Possibly this bottom halo here is a bit rarer than that, but you can see the gray dots show the scatter now from the whole population, assuming that dark light is a faithful reproduction of edge.
Yeah, cool. And on that note, what the underlying dark matter simulation that dark light's using? I was curious, how does its dark matter resolution compare to what you're using in Edge, and how important does it matter that they're comparable?
No, so that's a good point. So we've just used for this plot, we've just used the initial void volume before we do any zooming. So I think it's got a like 10 to the 5 solar masses per particle, so it's not exceptional resolution. It only needs to be good enough to resolve the growth history of these sort of 10 to the 9 halos. But that's the main reason why this plot stops here at 510 to the 8. It's because the void volume is not high enough resolution to go left of here. So we're planning, one of the many things on the to-do list is to run the void volume at high resolution, so we can go leftwards. But I'm also worried that I don't fully trust Edge over here, because once you're over here, you're into sort of first stars territory, top 3. You're forming a 10 star particles in the galaxy, and you really, it starts to get a bit hairy, shall we say?
Yeah. Cool. Thanks again.
Sure.
Okay. Thank you very much. So I don't see any other hands up. So last call for question. And if you don't have, I would like to thank you, Justin, very much. Great talk.
Sure. Thanks for having me.
Thank you very much for accepting the virtual seminar that sometimes with the Zoom fatigue.
That was good.